Sweet. All right, we're going live. First time doing a Zoom call. I don't know who's all in here yet. Trying to get my situation set up, but welcome, folks. Taking a minute to get up. Yeah, I think we're up. Got way too many windows open. It's hard to see. Yeah, I think we're good to go. Go for it. Sweet. Okay, so I do want to say something that's kind of funny. I didn't plan this out. Whenever you're doing the talk, just to be like totally transparent, they'll be able to on the stream. All the audio comes through my mic and doesn't go through the YouTube stream. So anybody on the YouTube stream, apologize for the awkward first couple of minutes. But my name is Austin Lovelace. I'm an engineer at Stuzo and a AWS Community Hero. And Kevin just gave an intro for everybody on the YouTube stream, saying basically that we're going to talk about AWS's Kubernetes offering EKS and do a small short intro on monitoring with Prometheus and Grafana. If you want to keep going, Kevin, go for it. Sweet. Okay, great. So this is a little bit awkward to cover streaming on YouTube and streaming on Zoom at the same time. So I think we're moved past that part hopefully now, but with you talking and not me not being able to put that audio through to the actual stream right now. But um, anyway, so Kevin Tin, cloud application architect at Worldwide Technology, recently became a community builder for everyone on YouTube stream. All right, let's move into Kubernetes. So um, basically, like, I guess the reason I want to do this talk is like recently I've been working a lot more with Kubernetes lately at my current company. At Stuzo, we run a few microservices, all managed by Kubernetes, and so I've been getting a bit deeper into it, and I've always wanted to do a talk about Kubernetes. So I was on Kubernetes running on inside of Raspberry Pis and managing three Raspberry Pis and having a little small application that connected to AWS as well. So for this talk, I wanted to go a little bit more in depth and talk about like what is Kubernetes as a whole, with AWS using EKS, talk about like what a container is, and how that differs from a VM, and then kind of talk about like the overall like landscape of how Kubernetes and EC2 and Docker, all that kind of work together, at least at a high level. And then at the end, we'll discuss EKS and Prometheus. This will be pretty introductory hack between everything. So the Prometheus Grafana, we'll do some basic monitoring within that. So also, if you guys have any questions, like feel free to put it in the YouTube chat or inside of the Zoom chat, and I've got everything open as best as I can to try and respond. Yes, if you guys have any questions, like feel free to post them in there, and I'll try to stop. And this could be like ad hoc. Whenever you have a question, we could talk about it. All right. So first off, I want to talk about what is a container, because the container is like the lowest level of what we're going to be doing today and working with. So a container is a form of like basically virtualization of an operating system. So we're going to take like an operating system like CentOS or Debian, and we're going to be able to replicate that on top of a virtual machine or on top of a actual like bare metal instance. And so what I have here is it's a package of all the code and dependencies to allow an application to run from one environment to another. So this like makes it easier whenever you're working with a larger team and you want to make sure everybody's working on the same software. You can use Docker or any other container services to package up your code, and then whenever they pull it down and run it, it would be the same as what it is on your machine. The container image would be the template file that is used to actually build the container itself, and then the image becomes a container at runtime. So here I have this like really basic diagram to kind of give you a visual of how this would look like. And so we have the hardware, which would be like your bare metal, or in the next slide we'll talk about like VMs, and then the host OS, our container engine, which is going to contain the logic to actually spin up the virtual operating system, and then our application would run on top of that. So then what's a virtual machine? Kind of similar in the sense of we're virtualizing our environment, but instead of just taking the actual operating system and that alone, we're going to take the entire hardware as it is and virtualize all of that and put that on top of another actual piece of hardware. And we're able to separate this with a hypervisor, which is, it could be hardware, software, firmware, but AWS has this tool that they like to use in-house called AWS Nitro system, which not all of their instances use this, but I think that they're moving towards that. And this could be like kernel level logic that's used to partition your CPU and memory so that you're able to say each virtual machine has this allotted amount of resources from your actual hardware. And so then you're able to separate and have multiple different computers that are basically just files on the computer itself or on the hardware device itself that are separate from one another. So then the difference between both of those, I kind of alluded to a moment ago, is your virtual machine is a packaging of your entire hardware device itself, along with the host OS and everything else. And then we would install a guest operating system on top, which would be where our virtual machine runs, and we can have applications running on top of that. And then our containers would be a little bit different, where it would just be the actual operating system, which would be run by a container engine like Docker. And then Docker would have its like proprietary software, or I guess Docker, and it would be able to separate our applications out into being smaller chunks that we can then reuse and package up so that we can have like the same application over and over again. And this is good for sharing between your teams and having everything about the same. So then here's an image of what that would look like if you could picture it from a visual sense. So this is how EC2 would run. So you could think about EC2 as like inside of AWS, they have these availability zones, which are just large data centers. And these data centers have a bunch of like racks of servers, like physical devices. And these physical devices have this AWS Nitro that's running to separate the CPU and memory and like allocate it dynamically per different instance type that were given by AWS. And then whenever we come in with our containers, we're taking the container engine on top of EC2, which is already a virtual machine, and making another abstraction layer on top of that. So then we have like, you could think of three layers. We have the actual hardware, then we have the virtual machine, then we have the container, and then we have, I guess, another layer, which would be our actual application split out on top of the container engine, which would be our actual containers themselves, our applications. So why would we need like container orchestration whenever your application is growing to a certain size and you have multiple containers? It becomes challenging to constantly set up, I guess, a way where you could update, manage, and deploy your applications. So you would want something that could come in and help manage like your networking, manage like the way that you're deploying applications, keeping applications alive and healthy. And if they aren't alive and healthy, alerting you, which comes in with Prometheus and Grafana. And so we would need some way that just kind of consumes and collects all these resources together so that we can better maintain our application whenever it gets to a larger scale, whenever we have like a few dozen microservices. So container orchestration is a good tool for this to help you organize everything whenever it gets to be at a larger scale. So then what is Kubernetes? Essentially just that. Kubernetes is a way to orchestrate your containers at scale and allows you to pull and group all of your resources together, all your different containers. And then you would have basically however you would want your application to be in its desired state, where you would say, I want like, I don't know, for redundancy, multiple different versions of the same application so that if one application goes down, the other one is still there. And I want several applications and they all talk to each other and they have this all internal networking. Then I would set up a Kubernetes cluster at whenever I get to a large enough scale to say, hey, can you please manage all of these different moving parts? And so this is whenever Kubernetes would come in and manage all that for you. And this is my taking an example from previous, whenever we had our EC2 instance with our we had our hardware device with the virtualized EC2 instance with the container engine application. And so then your Kubernetes cluster would manage the different nodes that you would have a part of your cluster, and then the actual software within that. So moving forward with what we just said about Kubernetes and the clusters and the nodes and the different jargon that comes along with that. So a cluster is just a group of nodes, which in this case for AWS would be EC2 instances. For the last talk, it was more Raspberry Pis, and we were just using bare metal and installing everything manually. So for Kubernetes, we're going to spin up a few EC2 instances, and we have a couple different options within EKS between Fargate, managed instances, or just doing it ourselves. For this demo, I will use managed instances, which we'll get into that a little bit more in the future. Then we have namespaces, which are virtual clusters backed by the same, like separate different environments or users or applications from one another. Like, for example, whenever you first spin up a Kubernetes instance or a cluster, it will provide you with a namespace of kube system, which is where all of your Kubernetes like specific components are run at. And whenever you build a new application, you want to probably use a separate namespace to separate it from the core services within Kubernetes that are running. And so you would have a new namespace be like your application, like for the demo, I called one crypto, for Prometheus called one monitoring, and for another application I have completely separate from the crypto app, it's called just app because I ran out of creative ideas. And the nodes are the actual physical or where we had the Raspberry Pis or the physical machines or the virtual machines being the EC2 instances. And these run pods. And we'll get into what those are in just a moment. But each node we have two different types of nodes. One node would be the worker node, which is managed by the control plane. And the control plane node contains the necessary resources to be able to allocate and deploy your pods to the correct place. And I'll explain those in just a moment. So with the control plane node, we have the ability to schedule applications, handle traffic, build the desired state of your application, giving like a certain specification of like what we want our application to look like with how many pods or containers, or whatever it may be that we have, that specification from the control plane and actually run that. And so then they run all of our applications with pods And then, yeah, of course, like nodes can have several pods. So back to our previous example of our multiple layers of abstraction, you could think about these nodes as another layer where you have a node as like a larger layer, and then you have a pod within the node or multiple pods. And you can also have multiple containers within an individual pod running as a sidecar if you're doing monitoring or whatever it may be. So that moves into getting more explicit about what pods are and the type of pods that we have. These are called objects. An object at a high level is called a record of intent. Basically what this means is you're going to create you could do it with either like a curl request to the Kubernetes API or with YAML or JSON. And you could have a specification of, I have this container I want to run, and I want it to be spread across multiple pods, and it needs to have like this much storage, this much memory, this much CPU, and I want to have all of that specified for this application because these are the dependencies that it requires. So you would define that typically in YAML or JSON, and you'd use something called the kubectl. But before we get into that, whenever you're creating a Kubernetes object, you can perform CRUD operations on it. So create, read, update, and delete using like Kubernetes API, which is a RESTful API. And this exposes an HTTP endpoint so you can deploy your objects. So like I said, our objects are defined using YAML or JSON. And then kubectl stands for kube control or Kubernetes control. And it's a wrapper essentially around the Kubernetes API, which allows you to write simple CLI commands to interact with the API and deploy your resources or whatever it may be. So that makes it a bit more simple. And the commands would be like kubectl get nodes or get pods. So that'd be like a pretty easy way of like looking at read operations, or kubectl apply, and then you could pass it a file as an argument. And that file would be like JSON or whatever it may be, or YAML for what's going to be in this demo. And it would deploy that application as is. And we'll talk about how that works more in depth here in a bit. So been saying pods quite a bit, explained a bit of what they are. I guess the definition would be that pods are the smallest deployable unit of computing that you can create and manage in Kubernetes. A pod is a group of one or more containers with shared namespace and shared volumes. We talked about the namespace earlier, so we would have the namespace, and then we would have pods within that namespace. And that namespace, beyond our nodes, these are like this is a virtual separation, share a volume. So if we were to set up a volume within our pod, we could have a container that would share that volume as well. So it could be like with a config map or whatever it may be. If you wanted to share that, it would be on the same physical or on the same virtual space. And then a deployment describes how to deploy updates for pods. And we have two different deployment styles, like a canary release in some kind of way where you could specify, okay, I want to have exactly this number of applications running at any given time because I can't afford to have any kind of downtime between my pods rotating out, and I want to have this many be replaced at any given time. And so you can specify all of these with the rolling update, or the recreate would be if you needed to just completely wipe it out and build a whole new set of pods at once. Recreate would just tear everything down and build the whole thing back up with a new container that you have. And then a DaemonSet works to ensure a pod is copied across all the nodes or specific nodes. You can specify that with labels, and we'll get into what that is in just a moment. An example of this would be log collection, daemon that runs on every node. So if you had, like later on, I'll talk about a node exporter, which is this daemon that runs on every node to get data from my EC2 instances on my CPU or memory or whatever it may be, and those metrics, and send that to Prometheus, and so they use a DaemonSet. So then we have a ReplicaSet, which is a replication of one pod multiple times until it terminates. We have a few jobs that run. They basically just query a third-party API to get cryptocurrency data and then send it to a different service within Kubernetes. And once it runs, it quits out, and then it's on a timer to run again. So you can kind of think of like a cron job, but that is actually a different resource that Kubernetes came out recently. So then we have secrets, which are mounted onto one or more containers. And these store sensitive information, like we store AWS credentials there possibly, or API keys or passwords. Then we have a config map, which is another volume which would be mounted onto your container. This would store information that's not confidential in a key value pair. This would be used for like environment specific configuration. For example, in the application, we're specifying whether or not we're going to query Bitcoin or if we're going to query Ethereum or Litecoin in our cryptocurrency application. So this is where we specify those different things. So then labels and selectors, mentioned those for a second earlier. This is going to be a key value pair attached to our objects. So inside of the JSON or YAML file, we're going to say we have a label of like Grafana dashboard or Prometheus or whatever it may be to like specify this belongs to this overall thing, or like label what this actual object is. And we could use this for associating objects together and filtering. So you would also use this whenever you're attaching services, which is the next thing. And services is an abstract way to expose an application. So it gives each pod its own IP address and a single DNS name. And the default for that is kind of what I have listed here. So you would have the service name, let's say it's called crypto-service, and then the namespace would be crypto, and the rest of the domain name would be .svc, which stands for service, .cluster.local. So this endpoint would be what our other applications inside our Kubernetes cluster could use to make HTTP requests to one another. So if I have in my crypto application a job that runs that pulls down the data from the external API server that then, or a different service, different container, different pod, all the same for what I'm trying to explain, and it then sends that data into a different database, we make that request between pods with the service, and the service domain name is going to resolve to this. And you could change this, but this is what the default ends up being. So then moving another step beyond that is Ingress. So this is a way to like expose our services. So if I wanted to make it so that I could make these requests outside of just the container or just the cluster itself and in the public internet, I can make an Ingress object, and for AWS purpose, an application load balancer, and the application load balancer would then resolve down to my service, which then the service would be able to say, hey, this where this request was coming from, and then route it appropriately to the pod that it is intended for, and then the container. So going into that, how that works is with an Ingress controller. So for an Ingress or an Ingress object to work, the cluster must have an Ingress controller running to manage the incoming request and route them to the correct place. And this is kind of what I'm talking about with being able to traverse through those multiple layers of our abstraction to get to our container itself. And the Ingress controller will take the request in from our Ingress object and map that to the correct service and to the container itself. And the controllers are not a part of the cluster automatically, so you'd have to go and install another Ingress controller or whatever controller works best for you after you've deployed your cluster. So for this demo, we are using the AWS specific controller for connecting with load balancers. So whenever you create an Ingress object, AWS creates an application load balancer. Whenever you create an service object with the type of load balancer, it'll create a network load balancer for you. So you have a little bit of flexibility between the different load balancer types you use. So before we move into that, anybody have any questions about the different object types? Go ahead and post them in the chat. Take a couple of minutes. It's kind of high level, just getting our definitions out. I'll go in and show an actual example of all of these and show it in the with kubectl, and then show the application running and show how it all connects. If you have any questions now, go ahead and post them. They're pretty abstract, but to kind of get into the nitty-gritty architecture itself, like how we talked about earlier, we have two different nodes. One is the control plane node and the data plane node, or the control plane and the worker nodes. So the control plane node consists of 4 different parts. etcd, which is a key value store, and that's easier to represent and talk about while we're looking at it visually. So etcd is a key value store, and this is where all of our specific information about Kubernetes and our cluster as a whole is stored at. Kube API server, or the Kubernetes API, is the RESTful API that's going to be exposed. KubeController will make sure that our application stays in its, or like works to make sure our application stays in its desired state. The scheduler makes sure to schedule certain pods wherever there's resources on certain nodes. Then we have, outside of these boxes, kubectl and our load balancer and everything. This would be like if users were to hit. So kubectl is outside of any of this, and the reason for this is open, like open through the internet, making basically like kubectl then takes those requests or services I would run. Then kube server sends, which is, think of it like a node agent that runs on each individual node itself. And then this takes it from the kube CTL through the API server to kubelet and says, okay, cool. So you want to have a pod, have 3, or have like a ReplicaSet. There's 3 of them. We have our crypto application. And then this says, okay, now on and schedule and actually like deploy that onto our node itself, and then run the pod. And then we have our container runtime, which is where our actual. And then, yeah, this over here, we would have end users making requests through the load balancer. It'd be like application load balancer. It's not illustrated here, but you can think of like a couple layers of an ingress object, and then a service, and then the service would route to the pod, and then the pod would make that request to the container. So go a little bit more in depth with this. So like I said before, kubectl is a wrapper around the Kubernetes REST API. etcd is a distributed key value store that holds and manages all that critical information about the Kubernetes cluster. The control manager is a daemon that runs constantly and evaluates the current cluster state versus the desired state. And the scheduler is responsible for scheduling pods to worker nodes. So kubelet's the node agent, which kind of like binds together the control plane and the data plane, or the worker nodes and the master nodes. And it runs on every single node inside of our cluster. And actually, if you look at the EKS optimized AMIs, the EKS optimized like Amazon machine images, I think is what AMI stands for. Those come pre-configured with kubelet and everything else installed and set up for you on that cluster, and that's why they're like optimized for EKS. You don't have to go through and set that up. If you ever set up Kubernetes on your own, you have to go into each individual instance and install a bunch of things. So AWS does optimize for EKS part. A little bit of a tangent. Kubelet is responsible for launching the pods. It does this by receiving a pod spec in either YAML or JSON that describes the state of the pod. Like I said before, with receiving that, we have one replica set, which has 3 replicas. And then, so yeah, whenever you write CLI commands using kubectl makes a request to the API server. API server then sends that request to execute on the Kubernetes objects via the kubectl. And that's how everything communicates together, so that you have control plane separate that manages the worker nodes. So then a couple other pieces of our worker node or data plane architecture is we have kubeproxy, which is a network proxy that runs on each node. It manages the internet traffic coming into your cluster and interacts with the service object to route to the appropriate container. And then we have cAdvisor or container advisor. And this is an open source agent that is integrated with kubelet that monitors resource usage and analyzes the performance of containers. And you can actually access these metrics if you're running a kubectl top. And we're going to be, this is one of the things we're going to be monitoring with Prometheus, is cAdvisor, and seeing the different metrics that are coming from that. So What is EKS? Bringing everything together. Talked about our containers, talked about what Kubernetes is, talked about the Kubernetes. So EKS is an AWS managed Kubernetes service. What this means is that EKS runs and scales Kubernetes control planes for you. They actually separate that into a separate VPC. So whenever you deploy an EKS cluster, you're not actually going to be in control of the EKS control plane or the worker or the master node. That's going to be in a completely separate VPC and a separate AWS account, completely managed by AWS itself. And I have a diagram that explains that a bit better, so I won't go super deep into that. But EKS is also good, integrated with AWS services like Elastic Container Registry, load balancers, VPC, and IAM. And EKS automatically upgrades your control plane for you, which is a big plus instead of having to go in and upgrade all the individual pieces between etcd, the controller manager, scheduler, and the API. You can just let AWS handle all that for you. So how this architecture works with one VPC to your customer VPC. So you can think about this as the Amazon VPC, and yeah, okay, so my diagram does a good job of explaining the difference. So whenever we make a request to our kubectl, it hits a network load balancer, which hits the control plane, like we showed earlier, which is which would be the API server in this instance that it hits. Then that can the API server reaches out to our kubectl or kubelet over an ENI, an Elastic Network Interface that's attached to our VPC in our account as a customer, and then does whatever it needs to do to our worker nodes. So this is the separation between the two VPCs that connect together, and it's over this ENI that EKS automatically sets up for you. And then if you had any clients that were going to connect, it'd be through a load balancer and the ingress and service to the pods. So this is a really key point of like the difference between running your cluster on Raspberry Pis or something like that, or managing yourself and letting AWS manage it, because they try to do their best to make sure that your control plane is highly available and won't go down, because that is the brains and the core of your entire Kubernetes application. So whenever we're running kubectl commands, to go a little bit more in depth from this slide, talk about the network load balancer, AWS makes a endpoint for us to hit. And so how we hit this endpoint is with, basically we have this endpoint that AWS builds for us, and we have a certificate that they give us, and we can settle this up in our local configuration whenever we're setting up our kubectl. And this configuration is called a Kubernetes config or KubeConfig. And so whenever we set this up, we give it our details about what our domain name is for our cluster, what our certificate of authority is to say that we have access actually doing anything with this. And I'll like show you that in the demo, like how we actually set that up and what that looks like. And so we're making that request over to the API server, and then that API server hits an ENI and is able to interact with our kubelet and then deploy our applications to our pods. Okay, so I posted the repo in the chat. I'll go ahead and do it again. Anybody who's missed it, it looks like it's still there in the YouTube chat. If you guys want to follow along or clone this or whatever, if you're getting into Kubernetes and you want to have like a resource to go by, it's like a decent resource to at least reference how certain objects are created or just like syntax and everything. So definitely check that out if you guys are into it. But we're going to go ahead and look at how everything's set up. So first thing, we should start off with the AWS console. So inside the console, we go to EKS. And if you guys have any questions, like just post in the chat and I'll answer them pretty much ad hoc. So we're not going to deploy a new cluster. It'd take a bit of time and we'd have a lot of dead silence going on. So I already have a cluster deployed called Crypto Cluster. Probably could have been named better because that's more than just a crypto application here, but it'll work for this demo. So we set up, we have 3 nodes inside of our cluster, and see right now it's asking me to upgrade this, and all I have to do is do update now, and it'd be a lot easier. So that's one of the perks of using the EKS Managed service. So right now I have 3 different nodes. I've selected them to be all T3 mediums, like pretty small. There's a good sizing reference I don't have available off the top of my head for essentially you'd want to size your instances based off how many pods you have because each pod needs its own ENI and instances can only have a certain number of ENIs. And so there is like a size your instance types. That may be a little bit beyond this, but it does exist. So our workload, we can see within this, I don't have any other applications running. I'm going to deploy those in just a moment. But this is the basic setup within Kubernetes that we have right now. Whenever I set up my EKS cluster, it came with most of this. And then I went and installed the AWS load balancer controller. And in the README, I don't have it set up yet, but I'll add instructions for how you set all this up. And so you could just replicate everything that I have here. So we could see our workload within this, or we could use other services like Lens, or just use the CLI. I think they're trying to get better at making it so people could use this. And then our configuration, this is where the endpoint for API server is, and you have different modes of setting up this API server. For this setup, I have this as public. So this, let's see, right here you could see it's open to the world, public. You would need to copy the certificate of authority and do a couple of things to make it so that you could use it. But this is how we're connecting right now, is hitting this endpoint through our kubectl certificate of authority saying that we have access to it, and then we're able to deploy objects. Talk about this, so our node group networking, I have in the repo a VPC that has 2 subnets, or 4 subnets, 2 private, 2 public. So all of our application actually runs inside of the private subnet, and then we have a NAT gateway with our load balancers inside of the public subnet. So whenever traffic comes in, it doesn't actually hit our individual pods or containers themselves. It goes through the load balancer, through the NAT, and then to our service itself, so their application is more secure. So this is the basic setup of that, and I'll add details into how you set that up into the README. But the VPC endpoint, or the VPC CloudFormation template, is in there. And then last thing I'll talk about with this is the VPC CNI. This stands for Container Network Interface. This goes a bit beyond how deep I want to go with this talk, but essentially this allows for every pod within your cluster to have its an IP address that is still within the CIDR range of your subnets. A little bit network heavy and a lot to unpack with that. Could have a whole talk on just that. So this is basically our Kubernetes setup for our EKS setup inside of AWS. I'm going to go to EC2 and get this window open, and we're going to watch a couple of things be built with load balancers. So nothing yet. So inside of our application, I have a couple of apps. We're not really going to talk about these too much, but cryptocurrency and animals. Essentially, this just has a client that makes a request to the server, and the server saves a new animal and state inside an array. Really basic, just kind of like get your feet wet with Kubernetes. We're not going to go super deep into this. This will be part of the README, like more tutorial of how you set up EKS. This kind of goes into the actual CloudFormation, and then this is IAM roles you need to set up with your Kubernetes cluster. And then load balancer controller, we're not going to go into this, but this would be what you would need to set up your load balancer controller, these 2 things. But what we are going to go into is animals, cryptocurrency, and Prometheus. So in our animals application, we have a namespace we talked about, which is our like virtual cluster. We're going to call this one app. We have a service. And here's our metadata. So we've got the name of the service and the namespace that it's within. Selector, which is going to be app and client. This goes back to our labels that we have. So our labels are going to be app and client. And so our service knows to send requests coming from port 8080 to this application. And this is a key thing to talk about with how these ports are set up. They're kind of confusing. So the difference between these three ports is really important whenever we're setting up a service. And I'll explain what this service object. So for this service object, we're having it frontward facing of this client application. And this client application runs on container, which is the target port here. And that's there for a reason. So essentially, within the cluster itself, port 8080 cluster would make requests to port 8080, and that would be then resolved to the container running on port 3001. And so whenever you see target port and you see my container, they're going to line up all throughout this repo. So then whenever we have our node port, this would be the port that we could, if my EC2 instances were public, for example, this would be the port, or if I were on a VPN or whatever, this would be the port that my application would run on my node itself. So to show you, if we do kubectl get nodes, it'll return us back a few nodes and their IP addresses. And if I went to the IP address of this and then went to port 80 or 3001 or 30,001, that would be displaying this service, which would show this application, essentially what that's doing. So we've got a couple services in here and a couple deployment types, which are going to deploy these pods, which have our container of our server for our animals app and our client for animals app. Whenever we set up communication between pod to pod, this is kind of a complicated topic. So like I said before, you have your service object, what IP, it's going to be the service name. So my service is called server-service, server-service. And then my namespace is going to be app, and it's going to be svc.cluster.local. So I put this here for a reason to kind of reference it close to this environment here for this container. So you see we have this container spec. We're giving it a name, telling it the image, telling it the environment. So within the environment, we're specifying two values, one or two key value pairs. The name for the first one is going to be SVC, which will reference the service. You can see that there. And the second will be namespace, which will reference here. So this is how I'm setting up domain name resolution between my two pods running in this Kubernetes cluster. So really quickly, if we go on to our animals application, this is really important to understand, especially if you're going to have like pod-to-pod communication, which most applications probably will, especially in a microservices architecture. Inside of app.js, I take these environment variables, which come through just whatever for your language. For Node.js, it's going to be process env. So I'm going to take process env.svc, which stands for service, process svc or env and the svc cluster local, and then the endpoint that I'm trying to hit, which matches my endpoint here. So in your application, this is really important of how this would connect. And so you'd have to work with your developers or whoever is going to be writing your application code, if it's you or if it's somebody else, to make this so that this would make sense. And we did this in a better way in this application, in the client app, where this is with Python. And inside of our Python application, instead of having it where we have endpoints that are or environment variables that are very specific to Kubernetes, we have instead settings.api URL. And so we just overwrite the API URL inside of our template here, inside of our spec. And I'm going to jump over to that. Sorry, a little bit bouncy, but I think this is an important concept to understand. So inside of our client application, I just went ahead and like wrote out the actual full length domain name. And these are variables that are actually available to you within Kubernetes, but for demo purposes, you could set it up like that, make something a little bit more fancy for service discovery, or you could just hard code the actual name, because this won't change your service name explicitly. And unless you change your namespace explicitly, like this will always be the same. So you could just hard code it. And that's how pod-to-pod communication works between service to service, and then is then translated down to the pod layer. If you have any questions on that, definitely post something, because that is a concept I found pretty challenging to wrap my head around at first. So we have our animals application. Like I said before, we got a namespace, we've got 2 services and 2 applications. We also have an Ingress type at the bottom. This Ingress type is going to build us a load balancer, and we have 2 services, and an Ingress references a service. So we have two Ingress types, one for the client service, listening on port 8080, which was the port exposed by our service. If you look back up here, right up here, port 8080. So our Ingress type is going to service name, and this is how it's going to route traffic to the correct object inside of Kubernetes. Also an important thing to understand. And then this is all specific annotations. So these are going to be like specific labels that we're going to add for our Ingress controller to know what to do with it. And this is like within AWS load balancer controller, the logic for all of that. So I'm not going to go in super depth about that, but basically we're going to specify these specific annotations to say this is going to be an Ingress class of an application load balancer. It will be publicly faced. We're going to be targeting some instances, and then we're going to add it to a group. And the group name is going to be app ingress group, and the group order will be 1 for this, and my group for order. And I didn't specify a port for this one down here because the default port is 80. And so since I'm listening with this for 8080, I did specify it. And the reason I did any of this is I didn't want to have multiple application load balancers to save on costs running for my same application. Why not just have it on different ports or different paths even? You could set it up like that, which is what this is here. This is path-based routing instead of like doing different ports. So with my app ingress group, I can group together multiple ingress types, and then my application load balancer will know what to do with that. I'm going to go ahead and apply this while that's building. I'll talk about it and I could show you. Let's see, let's go ahead and get into kubectl apply -f. So this would be like my create command, pass the file, animals is a path, animals.yaml. So this will start building. So this is my group. They're all collected together. And then the order is something you have to select, which is going to be like in which order are these going to execute, which order is my Ingress controller going to say like send traffic to this one or send traffic to this one. And so that's all part of the application or the AWS load balancer controller that you have to specify. And so this is how my whole animals application will run. So what I could do now that I deployed all of that is I could do kubectl get all -in app. So I'm going to get all the resources in the namespace. This is like a shorthand for namespace app. And you have to specify a namespace whenever you're doing these commands, unless you're getting nodes, and that's not namespace specific. Otherwise, the rest of the objects are namespace specific. So then I have these pods that are running, and I have my ReplicaSet, or my daemon that has my deployment that has 3 replicas, and my server that has 3 replicas. And it says that these are all running. I've got 2 services which we defined. They're giving IPs on my cluster, and then these ports. And so this is the internal port. This is the external port, the public port, which is the node port that we specified. So now you can see that visually right here, 3002, port 80, and then my target port, which is my actual application, which is somewhere hidden in my files. So this is kind of seeing it all manifest itself on our screen here. So then we've got our replica sets, which is showing us our desired states. It's ready to go. And then our different services. So now we could do kubectl get ingress -in app. And then we see our actual load balancer right here. And if we wanted to go to AWS, we can see that they deployed this and it's now active. And if you wanted to go more in depth to see how this is set up, you can see the different listeners between HTTP on 80 and on 8080. And that's our two different applications. So we went to the endpoint. I don't have anything for my root. So if I went to server/animals, it just returns an array. It's a pretty basic app. It's nothing too fancy, but I can add some animals to it. So I could go 8080/client/add animal/giraffe or something like that. And it just returns like Axios crits, and it's a pretty basic app. So I'm going to send this a couple of times. So then if I go back, /server/animals, I see I have giraffe now. And there's different links to this because of, this is a little bit specific to application logic, but since I have 3 separate replicas running, and these objects are all persistent in each individual container state. That's why it's different, because some may be 1, some may be 2. One of them might not have any. So that's our basic application for getting started with Kubernetes. Definitely where I'd start if you want to have like a basic app up and running. This is the easiest one to get started. No external dependencies, not doing anything crazy, just the basic namespace service deployment ingress. So moving on, of an in-depth application is our cryptocurrency app. We'll deploy this one pretty quickly. We won't spend too much time talking about this, but we do have a few different object types inside of this we spoke about in our high-level overview. One of them is called a secret, and the secret is going to encrypt our data here, and this is just encrypted with, or this is just base 64 encoded, so definitely not secure. I wouldn't like put this out in the public. I don't really have anything behind this that's super confidential that I need to be concerned about. You could query my database, it's fine. But if this were like credentials for like admin access, like make sure that you use something else and don't put this in source control. You could use something like SOPs to encrypt this. A little bit of a deeper conversation there, but there's tools to make it so that this is safe to put in source. So yeah, I'm passing in my access key and my secret access key in base 64. This will be mounted onto my pod, onto my container. And I have a config map, and this is key value pairs. So I have my database name. We're using Timestream DB, which we won't go super in depth with. It's AWS's a managed version of a time series database. So we need to pass it the name of the database, the table name, and the region. So then we have a job, and the job has 3 containers on it, which we said this is a pod that executes and then it stops whenever it's done executing. So we passed it a few different environments between where it needs to send its data to. So it's making like pod-to-pod communication requests, and then this crypto symbol. And so I set up 3 different containers because I had 3 different crypto symbols I wanted to use and to display what it would be like to have multiple containers inside of one pod. And so this is 3 containers set up, and each container, the difference is the crypto symbol value. Okay, and then back up here, actually, this is how we're referencing our secret and config map. env from reference the client secret and the config map secrets. So then this will have my AWS credentials between the secret key and the access key, and then the credentials or the key value pairs it needs to access the actual database. Then we have another secret here for an API key. And this is just for a public API that you can go get access to. I think it's called, I forgot what it's called actually, CoinMarketCap, yeah, CoinMarketCap. You could go like sign up, make an account, and they'll give you a API key to set this up. So we can go ahead and deploy this. Cryptocurrency app. So while that's deploying, it's not going to do anything too much crazy from the last one, other than we have secrets and config maps now. So now you're seeing the next object layer of this setup and how we're going to attach secrets and configuration objects to our containers themselves. And then we're also, the difference is we're running a job where that has 3 containers. Now we're moving on to, while that's deploying and setting up, it's going to set up an ingress. And so, or actually this one's going to set up an ingress, so this may take a second. This is going to be a quick overview of Grafana, and we're going to come back to it in our monitoring section. But we actually use Grafana to monitor and display or visualize our data from, because in our time series DB, we have a bunch of data we want to display to show the different trends and prices between our cryptocurrency applications. And so it makes sense to put it in something like Grafana so we can visualize it and make graphs and project and see like what's going on with the actual cryptocurrency, since it's been going through a lot of changes. So pretty much we have another deployment, and we have a lot of env specifications here. I did change the admin username and password so that it would use the secret ref using these Grafana credentials. So I have down here for my user and password. And the other difference is we have volumes, and the volume needs to be here because there is data that needs to be persisted for this pod. If I were to delete this pod, that data is deleted. You can fix this with another object called a persistent volume mount, which we didn't talk about or define in this. And AWS actually defines a EBS volume, elastic block storage, and mounts that to your EC2 instance. That's very AWS specific, but in a little bit can make this so this would persist. So if you did accidentally delete your deployment, it would still stay there. So let's go ahead and deploy this real quick. And then it has a service and ingress so we can see it. Apply -f cryptocurrency Grafana. Okay. So this is going to be provisioning. We can do kubectl get all -n crypto. Okay, great. So we've got multiple different jobs running. I'm having some errors right now. This is a little bit of a known issue that I just wasn't able to debug, but it still will send data to our application. There's something going on with the server and with my API because it's a free account. So not really much we can do about that right now, but there should be enough data coming through to our Timestream DB that we can display that data on our Grafana dashboard, which is running. And so we can go back to AWS and see it provisioning, and it take a couple seconds for it to become active. But this will be listening on port 80 because we defined our service on port 80 and the target port 3000, which is the port that our app's running on, and then connecting that together. And how this is set up too, I can also share the dashboard with you if you wanted to go check it out. We can also see different target groups while that's going up. And you can see the target groups that it established in my Kubernetes application. These names came from within Kubernetes of my spec that I'm defined. So we can see the node port would be 30,001 and the different targets. Looks like I've got some unhealthy instances. Oh, no, they're looking good. Not sure what's up with that. But our application's up, so we can forget about that and go look at Grafana real quick. So Grafana is a visualization tool. Just basically, we can give it a bunch of data and it will make a pretty dashboard for us, more or less. It can do some other stuff, I'm sure, but that's what we're going to use it for. So I'm going to go ahead and log in. So I defined my username as AWS Meetup Group and my password. All right, so we can add our data source, and we attach Timestream to it, which I did that inside of this here, my Grafana install plugins. I told it to install the Timestream data source plugin. And here, I have an IAM role actually. So here's my role that it's going to assume and my region. And we can save and test, and it'll see if it can connect. Uh-oh. Let's see why we can't connect. Oh my gosh, my internet's, hopefully the YouTube looks good. Okay, what's our role called? Grafana. Cool. So actually what I'm going to do really quick, because I did have a backup for this. I'm just going to put in some access keys really quickly and show you guys. I'm going to put this off really fast. Give me 1 sec. I have a user that has access to this, so we can get through this little roadblock. All right. Okay, cool. So all I did is I had a user that had just read access or full access for Timestream, and I grabbed credentials from it and pasted it in here. So now that we have our data source set up, we can go to create our own dashboard. I'm not really great at creating these dashboards as far as making them look super pretty, but what I'm going to do is just to show some data, I'm going to go to Timestream. And like I said, Timestream is just time series DB. Go to my table, crypto data, and I'm just going to copy this very, very basic query. Let's see if we can get that to run. Get any kind of data going. Looks like we're out of luck. My application seems to not be sending data from that coin market cap application. That's fine. We're going to have a lot of Grafana experience in just a minute, so this isn't too big of a deal. But all we did was add Timestream data source and then created a dashboard unsuccessfully, but we'll create a better one here in a moment. So we'll move past that. So we've got Animals cryptocurrency both deployed. We talked about a bunch of different objects. We deployed a couple applications. So that's our EKS demo at a high level, and it'll be more in depth to be like more of a lab and a tutorial whenever I finish writing out. So the application architecture behind all of this, just to put a diagram behind it, is we have a VPC with a couple different availability zones, so it might not be one-to-one. Well, we have an internet gateway and a router, route tables, and then this is our security, goes through the NAT gateway. NAT gateway sends it to our load balancer, and our load balancer then sends that data to our private subnets, and the private subnets are where our actual application runs. And so then we have our pods and our replica sets, and these are different subnets and our CIDR for our VPC. So this is kind of the high level overview of like our network diagram for our EKS cluster. So the whole point of this talk, I guess, or at the beginning, was initially supposed to be about Prometheus, and it turned into be a lot more than was expected. A lot of information to cover between Kubernetes as a whole and EKS. So Prometheus is going to be how we can monitor this larger application that we have, because Kubernetes is going to be, something that we use for a larger scale app, and we want to make sure that we're aware of everything that's going on, especially if we have a bunch of different microservices and applications running all at the same time, and there's a bunch of different things that can happen. We want to know what happens and when they happen. So Prometheus is perfect for that, because it's a time series DB similar to Timestream that we just used, which is kind of why we use Grafana for that. So Prometheus scrapes or pulls. Scrapes is a jargon word. I just think of it as like it's basically read requests for what we're doing for Prometheus, or making GET requests to certain REST endpoints. So we're going to scrape metrics from these instrumented jobs. There's several different ones we could set up, but we're just going to have a few around our basic Kubernetes architecture itself for like monitoring the pods and everything. So they either can be pulled directly or with push gateway, or scraped directly or with push gateway. Push gateway is a service you would use if you had short running tasks like my jobs that just run and then quit and then run and then quit. Push gateway is a gateway that your application can actually send data to, where if your Prometheus runs on an interval, mine runs every 5 seconds to pull data or scrape data. If you had it to where it was running a short job, like something that was ephemeral, and then you could have it, and Prometheus scrapes the push gateway. So that's what the push gateway is for, ephemeral tasks, and they don't recommend using it unless very specific use cases like those short running jobs. So it stores all scraped samples locally and runs rules over the data to aggregate and record new data or generate alerts. So this would be like if we have data coming in and we have a bunch of 400 errors, we want to alert us about what's going on. Or we have higher latency than expected because we set up configuration rules based on the amount of data and the amount of latency that we typically have. So Grafana is typically used to help visualize and collect this data, although Prometheus does have a dashboard, or I believe is what it's called, not 100% sure, but we'll look at it in just a moment. It's not nearly as feature-rich as Grafana. Prometheus works really well whenever you're recording time series data. It is a time series database, and it runs as a standalone server with no external dependencies. So you don't have to worry about anything else. Prometheus comes as its own, and you can add things onto it. Prometheus itself is its own service. So a couple features and background of it. It's a free open source event monitoring and alerting system developed by SoundCloud in 2012. There was a couple developers who actually developed it and were sponsored by SoundCloud. I forgot their names, but the easier way to say it is that it was just developed by SoundCloud in 2012, and I think made open source into the public in 2016. It's a multi-dimensional data model, so you can have multi-dimensions, like multiple different things we can query off of between metric names or key value pairs, like different labels. Its query language is called PromQL, Prometheus Query Language. Time series DB collected over HTTP via push and pull models. The push would be the push gateway, and the pull is what you typically would use where it would make requests, like GET requests to your HTTP endpoints. And then it can discover targets instead of you explicitly having to say, hey, I have this service like we explicitly did in our configuration. You can have it so it's dynamic, and Prometheus always knows what services to hit and where to go, and we can set that up. And that's how ours is set up, and I'll show you a little bit about that. It's a bit complicated of a configuration, but Prometheus does offer that. And then modes of graphing and dashboarding support. So the architecture of Prometheus, see it, it's just going to be an image that we're going to place into a pod and have a volume. For Prometheus as a whole, it's got the Prometheus server, which we have at storage, which is going to be stored onto that volume, the PromQL, that query language, which we can use with Grafana or with the web client that Prometheus comes with. We can have alert manager set up, which can send out alerts like Slack, email, PagerDuty, whatever it may be. Push gateway is going to be where our short run jobs are. So this is going to be a way for our jobs, like those short running tasks, to send their data to, and push gateway will then be ingested by Prometheus server. Jobs and exporters are external things like the node exporter we'll talk about is something that's going to open up another endpoint that will grab a bunch of data from our EC2 instances and then expose an endpoint / metrics, which Prometheus server will tell Prometheus that endpoint, and it will pull all of that. And that's our basic, our service discovery is going to be how it's going to find different applications or services. It's so jargon heavy, it's hard to explain in a way that isn't like extremely high level. But this is going to be a way that it will find our Kubernetes resources and retrieve data, explicitly define what those resources are or targets. So the components, to explain this in more detail: Prometheus server, it's a pull model and it scrapes time series database or time series data. Client libraries, there's many of these. We can go ahead and look at this really quickly. So these client libraries are what we're going to use in our application, inside of our client applications, that will collect data and metrics about our application itself, and then we can expose an HTTP endpoint to Prometheus. And Prometheus has a few that they've built between Go, Java, Scala, Python, and Ruby, and then they recognize these third-party ones. And I'm sure there's others out here than just these. Like I know the Node.js one, I didn't use Prom Client. I used one called Swagger Stats, and I'll show you guys that whenever we get into it. So that's not listed there, but there's a few good ones listed there. And then we have Push Gateway. We've explained that many times. And then the exporters, these are able to receive metrics from non-Prometheus systems like our EC2 instances or like databases and stuff. A bunch of different options. You have a ton of options here: hardware related, database related, issue tracking, messaging systems. Like you could do Kafka monitoring, RabbitMQ monitoring. A lot of different places that we could set up external sources to then send our data into Prometheus and for Prometheus to query. So that's what that essentially is. And then Alert Manager handles alerts and sends them to services like Slack or PagerDuty. Okay, cover all those, yep. So Grafana allows you to query, visualize, and alert based on your metrics. It allows you to create custom dashboards like we've done, and it's open source, free to use. So this would be an example of a really fancy looking dashboard. I just took this image off of Google Images just to get something pretty to display, but this shows a bunch of different gears and graphs that we can look at and make insights on our data or make actions on, depending on if 71%, not sure what this is, but could be something that action might need to be required to take on it. So we're going to be monitoring 4 different resources: CAdvisor, which we talked about earlier, which is going to run on all of our different containers and provide us metrics on. Node Exporter, I actually didn't set this up, but it's worth talking about. Node Exporter will monitor the CPU, memory, and disk space on the actual node itself. So it's like the higher level from CAdvisor. Kubestate Metrics, this service listens to the Kubernetes API, and it will grab a bunch of information about specific objects between the kubestate metrics, or between Kubernetes. So like our services, our endpoints, our pods, our ingress, and it will expose those metrics to the /endpoint or the /metrics endpoint. And it's by default listening on port 8080. So then Kubernetes can then make a read request to /metrics on port 8080 and retrieve those metrics and ingest them. And then Swagger Stats, which is a middleware that will trace our REST API calls within our Node.js app. And that endpoint will be /Swagger Stats /metrics. So piggybacking off of that really quick, actually figure out what the endpoint is. So I already have Swagger Stats set up on one of these applications, on the Node.js one for the Animals app. So what we could do to see what that data looks like in this Timestream data is if we went to this and go /swagger-stats/metrics, this is kind of what our Timestream data looks like, our time series data looks like. So it's got just random bits of data that Swagger Stats has aggregated and put together and said that we've had 3 successful API calls, and apparently I've had 200 unsuccessful ones, and whatever else it may be. It also comes with the UI, and this is straight out of my Ingress type, out of my load balancer. All of this is displayed, so it's actually a really nice tool. So I have 97.77% error rates. That's pretty bad. It shows me my memory usage, my CPU, bunch of different metrics out of this. I'm not super well versed with this dashboard, but it is really cool. But let's set up Grafana and we can show you how Grafana takes all this data. All right, so back in here, I've got my Grafana set up and I've got a specific dashboard for it. I've got my kube state metrics, which, like we said, are going to monitor the Kubernetes objects. I've got the Prometheus namespace, which we're just going to call monitoring. And the deployment, this is going to be my Prometheus pod. We're just going to deploy one of them. It's got a few arguments you could pass into your container. It's going to run on 9090. This is another container that's going to run. That's going to monitor if anything changes with WeWorks watch. We have a few volume mounts because we are storing this is like a database essentially with a couple other features. So we need to store this data somewhere. So we have a few volume mounts. So we can go ahead and deploy or apply Prometheus namespace. Gosh, I've got this nested. All right. So we can apply the namespace, and then once the namespace is applied, then we can deploy the deployment. With these other services I had set up, I had them all in one big YAML file. This one's set up a little bit differently. It's a little bit more complicated. And if you were to deploy an object into a namespace that doesn't exist, you would get an error that would say that that namespace doesn't exist, which is basically saying you're trying to deploy it into a cluster, and it's like that's not a thing. So now I'm going to cd into Prometheus. And, oh, that's going to be. Okay, so our deployment's going to go out, and I'm just going to go ahead and deploy everything else too. My internet's going real slow. Before we get into this, we just have an ingress, same as all the other ones, a service, same as all the other ones. Differences, we have a couple, our load balancer controller. This just says like, yes, to scrape the service, and we want to scrape it on port 9090, which is Prometheus scraping itself. All right, so then kubectl apply -f Prometheus. And we should be able to do that, and it should apply everything else and say that some of these are unaffected, so it'll apply all of them. Yep. Cool, so namespace is unchanged, my deployment's unchanged. A couple of my role bindings are unchanged, which this just gives Prometheus permissions to access /metrics, and it's going to use the verbs get, list, and watch, so like our read verbs. Okay, so everything's deployed or is in the act of being deployed. Get all -n monitoring other than kube state metrics, I'll come back to. For that, this is our Prometheus YAML. This is a file that is going to be our config map, which you can store files as a configuration map. And this is just going to be like all key value pair. So the global is going to say that we're going to have a scrape interval every 5 minutes and evaluate it every 5 seconds. Then we have a few scrape configs, and these you can set up multiple. We have multiple jobs. I'm not going to explain this super deep, but what this is basically saying is, hey, we're going to make HTTP requests. We need to have credentials for that. So this is the credentials from Kubernetes. This is my bear token file. And then we're going to relabel these things. So how we talked about earlier, where we build a service and the service has a namespace, the service name, and then the .svc.cluster.local. Kind of similar. These different labels will be translated, and let's see, down here, we'll replace them to being like an actual endpoint. And so this will be the actual way that service discovery works, where it's like, okay, find this label and then change it, replicate it, or not replicate it, but modify it to be used to grab the metrics from my Kubernetes nodes. It's a bit confusing with the syntax. I definitely encourage you to like dig deeper into this. This could be like a whole topic on itself about service discovery, but the basics were taking this label and modifying this name, and this endpoint is then what Prometheus will use to data from. Okay, so we set up that Prometheus environment. Monitoring. So I'm going to get my Ingress endpoint right here, and hopefully by this time it has finished provisioning. Okay, cool. So this is Prometheus, the Prometheus dashboard. I think it's called Prometheus Explorer or Explorer dashboard, something like that. But we can write PromQL expressions, or we can have like metrics that we define here, like my Node.js process CPU percentage. This is actually coming from my Swagger stats slash metrics endpoint. And really quickly, the way that that's happening, sorry, is in my animals configuration, I have an annotation that actually defines that. And it defines the port, and it says, yes, please come take my data, use this port, and this is the container port, and this is what endpoint all my data is at. So it's already grabbing that data. We could use the graph, which I'm not super great with this service anyway, so we don't have to worry about that too much. It's that we have set up currently. We got the API server, our C advisor, our nodes, pods, and service endpoints. And so we use the service discovery to grab these to get the actual and the actual URL, and all of that is from those annotations that we set up. So then you could set up rules, which we don't have any. Rules would be like, hey, if this does this, then trigger some kind of action. Like if you have, latency that goes over 200 milliseconds and it does that for 1 minute, then that's an excessive amount of latency that we're not used to. So trigger a alert, which we don't have any set up. And then service discovery. You can see a lot of the different labels here, which this goes into the multi-dimension part of the database, where we can have actual metric names, or these like different key value pairs. And so this is going into a deeper part of Kubernetes, where it's grabbing a bunch of metadata from our what's it called? Totally blanked out for a moment. It's grabbing a bunch of metadata from our Kubernetes API, and the Kubernetes API is returning all of that back to our Prometheus server, and then Prometheus is then running the logic that we set up in our config map, and it's finding these different services. And if you actually went into the Prometheus GitHub, let's see if I can find it. Inside of here, I think it's inside of Discovery, Kubernetes. This is the source code of Prometheus, all open source. Okay, cool. So inside of Prometheus, in the source code itself, very similar to how I was talking about how we set up the actual service endpoints to do service discovery, it does the same thing. It grabs the service name, the namespace name, and then appends .svc And I'm not sure what this is. I'm not a Go developer, but I imagine it's the rest of the, just concatenating the rest of the endpoint together with whatever service discovery logic is going on. But it's the same thing that we have set up in our application. So it's cool to see the actual source code of how that's working behind the scenes. It's all the same thing. So, okay, great. So we've got everything with our basic Prometheus setup going except for Kubernetes, which I'll go ahead and deploy that. And then we'll deploy Grafana and we'll look at a dashboard and we'll call it a day. So KubeState metrics has a bunch of different things. I'm not going to go over the details of it. It monitors the Kubernetes API. So kubectl apply -f Prometheus KubeState metrics. Hope all goes well. Okay, and I'm going to go ahead and apply Grafana. kubectl apply -f Grafana YAML. And this Grafana template is the same exact one I used. I believe it's the same exact one. I don't think I changed anything that I used in my cryptocurrency application. Okay, great. Get all -n monitoring. Okay, sweet. So Grafana, Kubemetrics, Prometheus, and we've got a few services running. Got our deployments, which were all defined as Grafana, our different ones between Prometheus, KubeState, Grafana. Okay, great. So Grafana has an Ingress at the end of it inside of here. Like I said, it's the same exact template. I changed the node port, I guess. Otherwise, it's the same. And so this might take a moment to spin up, but get out of here. Yeah. Okay. So while that's spinning up, we can go to EC2 and watch it happen really quick. Okay, so this is our Prometheus. Look at that. We're having some things happen. Bunch of client errors. See the new UX, why not? Oh my gosh. Okay, sweet. This one's active. All right. Now we're going to go to Grafana. We're going to set up Prometheus as data source, look at a dashboard that's already pre-built, and yeah, we can make some insights out of it. Or not. Maybe it'll all be useless. All right. So, cool. Log in again. Oops. If you guys want to like log in and check this out as well, this is all, I set it up to it's all have read access. I'll post these in both of the chats. And you could also, I mean, any of these endpoints are public right now, so you can see any of these, but if you wanted to follow along with Grafana, you could at least see the read-only version of it. So I have Prometheus set up, and I set up my Prometheus with a public load balancer. This is just for demo purposes. You probably wouldn't want to do this in production, but I have this set up for Prometheus, so I can just paste in that endpoint into my URL. I'm gonna leave everything else as default and then save and test. So my data source is working, cool. So then I can go back here and it'll be like, cool, create your first dashboard. So we can add, actually, you know what we could do instead of that is allow somebody else to help us. So there's a few dashboards I found online, and Grafana has a Grafana dashboard, where you can go into Grafana, go to their dashboards, through what they have. Let's see, right here, and you can see like all these different dashboards. And this, I think this is where I got this one actually. Cube statements 315 is the name. This is being imported from grafana.com. We're going to select our data source, and it just gives us the name of what that dashboard was called. We can import that, and then we can start seeing some metrics on our application. We can start seeing things going on. It does have quite a bit of things in this dashboard. Some of them I don't have completely set up, but you get an idea of like how you could go in here and use this and set this up and use other people's templates. And then you could go from here and say, this I don't like exactly, and we could change it to I don't know, a gauge or something like that, and apply that. And then we have a gauge instead. And maybe that doesn't make as much sense for this, but just to give you an example, you take somebody else's, modify it, make it so that it's your own, and then we can save the dashboard. And then let's see, if we go to dashboard settings, then we can take the JSON out of it, and we could basically use that wherever. And then this JSON appears, and we can use this wherever we want and modify this if we want, or we can modify it in the visual, and then it will export it to JSON. And the last thing we'll do is deploy. So we can import one, upload a JSON file, where is our app? Prometheus, Grafana, dashboard. All right. So then we can import that, and we have a dashboard around our Swagger stats. It's not super great, but hopefully it shows us something. So I don't have a lot going on with it. Then we can play around with this and make it a little bit better. This is kind of just a high-level review of Prometheus and Grafana and how you would set this up and some templates to go along with it. So that's going to wrap up our very action-packed meetup. If you guys have any questions, like feel free to post them in the chat. I'll hang out for like another 5 minutes or so. If not, or if you want to hit us up offline, this is my LinkedIn and this is Kevin's LinkedIn. I don't know if Kevin's still on the call or not, but if you guys want to message us or have any questions right now, like go for it. And pretty much anything. It doesn't have to be Kubernetes or doesn't have to be Kubernetes or AWS specific. You got this far, but it didn't show any data in Prometheus. Well, that sucks. That's like the worst part. Maybe we could take this offline and go over it. I'm down to do a call and see if we can debug it. Sweet. Thank you guys. Thanks for the positive feedback. A little bit of a monologue. It's pretty awkward being on the other end of the call, I'm not gonna lie. It's like one of those things where you're like, yeah, like I don't know what to do with my hands. But yeah, thank you guys. Sweet. Yeah, Kevin's actually doing a meetup talking about presenting again in 2 weeks, I think, on green grass with IoT. So he's going to be talking about IoT at edge, like with a few Raspberry Pis and stuff like that. So that should be pretty interesting. Oh, he's back. I didn't even know you existed anymore. It was too much content. Sweet. Yeah, I guess we'll go ahead and close out. Thank you guys for coming. Everybody else is here. You guys are the winners. Staying this late, staying through an hour and 40-minute talk. That's like, especially like, whenever it's one guy just preaching more or less. So right on. Yeah, stay tuned. Check out the meetup in 2 weeks, March when is it? March 24th? Yeah. I'll go ahead and post that in here and then hop off. Unless you have anything to say, Kevin.